Hello everyone. This video is going to explain the answers to the Chapter 7 required practice test. So I'm going to assume that you've already got the data that you need for the first chunk of questions loaded into Gemovie, as I do here. The first thing you want to do is enter your value labels. So in this one, you're comparing people who are early birds versus night owls, people who like to get up early in the morning or people who like to stay up late at night. And they're labeled into groups as 1 and 2. So you want to label them so the output's a little easier to read. So double click on group. And as it says in the data file itself, the group 1 are the early birds. And the group 2 are the night owls. So you do this, and that'll make your output a lot easier to read. And you don't really need to do this yet, but I'd like to, before I leave this screen, I'd just like to get everything done that you need to get done for the Gemovie stuff. So you will eventually want to do a independent samples t-test on this. So you'll click on t-test, independent samples t. Your grouping variable, again, whether they're a night owl or an early bird, goes here, and your score, which is going to be their score on a final exam in a course, goes here, and you'll get your results over here. But this isn't enough results. We need a lot more, so you'll want to click on the mean difference, confidence interval, the effect size, its confidence interval, descriptive statistics, so you get the means and standard deviations, and then you'll want a nice plot right there. The other thing you're going to need eventually is a homogeneity of variance test right here, Levene's test. So by scrolling up and down here, that'll be everything you need. The other thing you should be aware of is how to change the test if you want a one or two-tailed test. We want a two-tailed test in this case, so this is set up in the right spot. If it's a one-tailed test, you'd want to change to one of these depending on your specific one-tailed test that you want to evaluate. Okay, so now that we have that done, I'm going to open up this screen here so we can see everything. All right, and now we're ready to look at the actual test itself. So here I have a Word document that has the actual test in it. And the first few questions, we don't really need the output, but I'll leave it set up like this for reasons that'll make it easier later. So in the first one, it's describing the scenario, as you know, and the actual question is, which of the following statement is the best description of the assumption of normality? And it's this one down here. The normality assumption is literally this answer. It's the distribution of sample means. In this case, the sample mean differences is going to have a normal shape. And that's likely to be the case here. And anyway, that is the assumption. Next question, you want to pick the two-tailed null hypothesis. The null hypothesis is always saying that there's something not going on. So it's saying that these two groups are not going to be equal to each other on their exam performance. So it's C here. The two groups will not be different on the exam score. And then this one, you just want to perform the graph and then interpret it. So if we look at the graph right here, we can see that the early birds seem to have a higher exam score than do the night owls. And so you'll want to pick that one. And again, that's why you want to have the labels in here. That way you don't remember who's 1 and 2, so that the labels are helpful. Next, you want to use software to find the group mean differences. Well, here are the two means, right? The mean of the early birds and night owls. Well, if you want to find the mean difference, it's right here, right? So if you subtract these two means, that's how far apart they'll be. So there's your answer. Next question, if the data are consistent with the null hypothesis, you'd expect the difference between the means to be 0, and you'd expect the t-statistic to be 0. And to help explain that, I've typed the equation for the t-test right here. Well, the numerator is the mean difference. So if the null is true, again, the null is expecting that the two groups won't be different. So if you subtract the two means, you'll get a 0. And then if the numerator, which is the mean difference here, is 0, then no matter what the denominator is, the t-test is going to be 0. So that's the logic there. Then you want to use use software to find the standard error of the mean difference. It's given right here, the SE difference. So that's why that's the answer. Now this one's a little tougher to understand or explain perhaps, but if the data are consistent with the null, you expect the standard error to be what? Okay. Well, so I guess a good way of thinking about this is to look at the t equation again. Think about what happens if the mean difference is about the same size as the standard error of the mean. Remember, the standard error of the mean is the amount of sampling error that you'd expect in the study. Another way of saying that is it's the distance that you expect the two means to be different from each other due to sampling error. It's how far apart you'd expect them to be different just due to sampling error. Well, if the mean difference is about the same size as the SEM, what you're saying is you got the amount of sampling error that you expected. So that's what a t of 1 means. The mean difference was about as far as you'd expect due to sampling error. About as far apart as you would expect based on the sampling error you'd expect. If you get a t of 2, that means the mean difference was twice as big as the sampling error you would expect, as the mean difference you would expect due to sampling error. So that's the reason why this is the answer it is. Okay, now you want to look at the Levene's test and find the p-value for it. Well, here's the Levene's test, here's the p-value. Again, that's not a very compelling p-value, so eventually you're going to conclude that there's not very much evidence to reject the null hypothesis that the two variances in these two conditions are about the same. That's what we're testing here. This Levene's test is for the homogeneity of variance assumption. And basically we're looking at the variability in the two conditions. One is about 10.7, and the other one is 11.2. Those are not very different from each other at all. These are very similar measures of variability in the two conditions, and that's why this p-value is so high. So you really have no evidence at all that the homogeneity of variance assumption is violated in this situation, which means you're going to use the student t rather than the Welch's t, as you did in that one assignment. Okay, is it likely that the assumption of homogeneity is violated? No, again, because this p-value is really large. Find the independent t, it's right here, the student t, it's 1.62 or 1.63. Find the two-tailed p-value, it's right here, p equals about 0.11. Then you want to find the d. Cohen's d is right here. It's a 0.5. That looks like a medium-sized effect. I should have mentioned that the p is not very compelling. It's weak evidence against the null. Now we want to find the confidence interval around the mean difference. Well, here is the mean difference, and here's the confidence interval around it. So those are your two values. Confidence interval around d, here's your d, and here's the confidence interval around d. Oops, 95% confidence interval, lower bound, upper bound. Okay, and now you want to kind of choose all the right numbers and put them into the right format. Here is the correct answer. So why are these all the right numbers and why are they where they are? A common mistake is people want to put the actual obtained t value in the parentheses. You don't want to do that. What goes in the parentheses is the degrees of freedom, which is right here. It's the number of people you have minus 2, number of participants you have in the studies. There's 20 people in each group, so it's going to be 38. So that's why it goes there. Then after the equal sign, you put the obtained t value. Then you put your p, 95% confidence interval for the mean difference comes next. And then your D, and then the confidence interval around D. Now I should mention that the confidence interval around D, the values are slightly different because in the when this test was made, we used a different program, JASP, and it computes the confidence interval around D slightly differently. There's a few ways of doing it, and this semester we're using JASP, and it computes it a different way. Again, they're very similar, so just pick the ones that are closest if they're a little off on the test or in activities like this. Okay, now you want to choose the best summary here. So the right answer is this first one. Everything in here is correct. So the night owls performed worse in the morning than did the early birds. That's true. You can know that by looking at the means, right? The night owls did worse on the exam. However, the p-value suggests the difference might be due to sampling error. That's true. The p-value is only weak evidence against the null. And this difference is moderate in size. That's true because the D is 0.5. And the confidence interval suggests that the true value might be very large to small in the opposite direction. This is the confidence interval, so it's 1.1 D would be very large. Again, 0.8 would be large, so 0.11 would be very large. And then a negative is in the opposite direction. It might be a very wide range. It might be a really small effect in the opposite direction, with the night owls actually doing better in the morning than the early birds. That's plausible. All the way to the other direction, where the early birds would do a lot better in the morning. So again, that's a very wide range. And so again, because of the p-value being not compelling and the very wide range, we should pretty much withhold our judgment on this and replicate with a larger sample size. The other thing that tells you that you want to replicate it with a larger sample size is this pattern that you have with a relatively large p-value and a relatively large d. If you have a large p-value and a large d effect size, that's a telltale sign that you should probably redo your study with a larger sample size. That pattern of data tells you that your sample size is too small. Now, I also pointed out here why some of these other answers were wrong. B is wrong because it says it's very unlikely to be due to sampling error. Well, this p-value is too large to justify that statement. It's also saying that the estimates for the population parameters like D are very precise. They're clearly not. The lower bound says it's a small negative effect, and the upper bound says it's a very, very large effect. That's a huge range. Everything between those values is considered plausible, so that's not very precise at all. It says it's a negligible effect in size and is almost surely due to sampling error. Well, I don't know that I would say it's that's true. You can't say that a D of 0.5, which is moderate, is negligible. And you know, it's weak evidence against the null. I wouldn't want to say that you're 100% sure it's due to confidence error or due to sampling error at all. So I don't like that combination of words there. And then finally, the night owls did moderately better. That's just completely opposite of the pattern that you got looking at the means. Okay, and next, you want to talk about what the p-value means. This is pretty much just a definition of the p-value, so you really do need to memorize this. If your obtained t-statistic were 1.62 and it's two-tailed test, the p-value is the probability that you would get a t-value more extreme than the 1.62 on either tail if the null is true. Okay, so if the null is true, how often would you get a t-value of 1.62? Well, it's the probability of getting something in this tail and something in that tail for a two-tailed test. So yeah, that's this again. The p-value is the probability of getting the obtained t or something further from zero if the null is true. And again, if you get a very small p-value, that's strong evidence that the null might not be true. Okay, a large effect size will always have a small p-value. Well, we know that's not false, we know that is false because of the previous example. And again, if you have both of them being large, that suggests you should redo your study with a larger sample size. Choose the best interpretation of the confidence interval. Okay, in general, again, the best answer is C here. It's a range of plausible values for the population parameter, and values in the middle of the range of the confidence interval are considered more plausible than those near the upper bound and lower bound. And the things that are wrong with the other statements are in bold. So the values near the lower bound are more likely than the upper bound. That's just not true. Values in the confidence interval are equally plausible. No, values towards the middle are more plausible than those near the tails or near the upper bound and lower bound. And values near the lower bound and upper bound are more plausible than values in the middle. That's exactly the opposite of what is true. Okay, standardized effect sizes are more useful than mean differences when you want to compare the results of the different studies used to different measures. So if one study is done in pounds and one study is done in kilograms, if you convert the standard, if you use a D, you can compare those things directly. And sometimes raw scores are not easy to interpret. Like if you have a difference in a 0.3 difference in a scale of depression, and you're not very familiar with that scale, that raw score difference might be very hard to interpret. And instead, you can use the D, because then you know if you get a D of 0.5, you know that's a medium effect because you have that scale, a standardized scale for interpreting D. So very often a D is going to be easier to interpret if you don't have a lot of knowledge of the raw score mean difference, how much of that is going to be important, or if you want to compare results across different studies that use different dependent variables. Okay, and this next question, you're supposed to read this and interpret the results that are provided for you. So you don't need JASP or anything for this. So I'll just go ahead and blow this up a little bit. So here we're looking at the probability again, I want you to look at the p-value. So here is, again, just pretty much a definition of the p-value. It's the probability of getting the obtained t or something further from that value in either tail. And so it's pretty much a definition. Okay, and then what I've done here is I've copied the stuff we need to be looking at for all of the next questions, so I don't have to keep scrolling up and down. So here is the information. Choose the best interpretation of the p-value. The best interpretation is D. People generated more solutions when they worked in a group than when they worked alone. And this difference is within what we would expect due to sampling error. We should withhold judgment on the results. And we say that because the p-value is 0.24. That's a pretty large p-value. That data is considered consistent with the null hypothesis. So again, it's correct that the people working in a group generated more solutions, a mean of 5.13 versus 4.43. So clearly that's bigger, but that difference is considered to be likely due to sampling error because the p is so large. Now I've highlighted again what's wrong with the other options. It's saying people generated fewer solutions than they worked in a group. That's not true. It also said that it's unlikely that that difference is due to sampling error. Well, the p-value is too large to make that statement. Second one, it says that people generated fewer when they worked in a group. We said that's not true. And the third one, again, says that the p-value suggests that it's unlikely we do sampling error, and that's not true. Again, I've put the relevant data here and highlighted it so that we can easily look at it. In this case, we want to know if we want to interpret the mean difference. And so really you just look at the means and find the difference. These were different by 0.7, so the people in the group condition generated 0.7 more solutions than those in the individual condition. And here it's asking you to interpret the standardized D. Well, the standardized D is 0.35. So you know that one group scored 0.35 of a standard deviation better than the other group. That's what D is in. D is in standard deviation units. So if you get a D of 0.35, that means one group did 0.35 standard deviations better than the other group. So B is your right answer. Okay, and here we want to interpret the confidence interval around the effect size. So this is what we're interpreting, these bold numbers here. A is the right answer. This confidence interval is very wide. It's very wide because it's going from, again, a small negative effect to a large positive effect. That's a very wide range. That's telling you that a small negative effect, a no effect, a small positive effect, a medium effect, or a large effect are all considered plausible outcomes. That's a very wide range of plausible outcomes. Okay. So, and A is saying all of that is correct. B, it's saying that the effect size may be anywhere between negligible and large. That's not true. It could be even a negative effect, so that's wrong. It's saying that the C is saying that the lower bound and the upper bound suggest the effect size is quite large. No, the lower bound suggests it's a small negative effect, so that's not true. And this last one says the lower bound and the upper bound suggest that the effect size is rather small. No, here's the lower bound. That says it's a small negative. Here's the upper bound. It says that it's large. So again, these are the confidence intervals. So everything between there is considered plausible. Your best guess at the effect size is D, however. That's the middle. Values close to D are considered more plausible than values close to the lower bound and upper bound. Okay, and now we want to make a final statement, make a conclusion about these results. So your best answer is C here. The groups did better than the individual groups because they generated more solutions, but the p-value associated with this difference is too high to be compelling. That's true because it's a 0.24. And the study should be replicated to better understand the results. And again, it should be replicated because we have a large p-value and at least a medium, or small medium effect size. That suggests that maybe we need a bigger sample size. Well, A has some wrong things in it. The results provide clear evidence. No, they don't, because the p-value is saying that there's really nothing to see here. It's just sampling error. But the D is relatively large. It's medium large. It's suggested that might have practical importance. That's inconsistent results. That's unclear. The P, effect size, and confidence intervals all yield similar results. That's not true. Again, as I've indicated, if you interpreted the p-value and the D, they would kind of tell you different. They would suggest different conclusions, and the results are consistent with the existing literature. No, as if you read the scenario, the previous literature would have suggested that we would have found a compelling p-value here, and we did not. Okay, again, same thing wrong with B as I've described in A. And D, again, the results are not clear. And also, it's saying that there is sufficient evidence to suggest that teachers should not require group work. Even though we didn't reject the null, this pattern of data suggests that, again, with a D like this, maybe we should do this again with a larger sample size. So I don't think it's a good conclusion to say that, oh yeah, there's this definitive evidence that group work doesn't work. More research should be done here. So they're not randomly assigned to condition. So if they're not randomly assigned to condition, you want to really not trust any of the results. And there's lots of things wrong with these other answers. The confidence interval, the upper and lower bound ranges, the random assignment isn't really going to influence the accuracy of the upper bound and lower bound. I mean, you're not going to trust the numbers, but they're not going to be wider or narrower based on that random assignment. And then the central limit theorem has nothing to do with controlling for lack of random assignment. And clearly these results are not going to provide compelling evidence. So yeah, B is your best answer. Okay, now we're going to interpret the p-value. Here it is, and you would expect this outcome to occur about 0.03% of the time if the null is true. And that means you're going to get a t-value of greater than 3.78 or less than negative 3.78. Should be a negative there. That extreme or further from zero, only a very small percent of the time. So this would be a compelling p-value. So that is your right answer. Again, it's a definition of the p-value. Select the best interpretation of the effect size. In this case, the effect size is a d of 0.8, which is a large effect size. So this is your best answer. Your standardized effect size is large, and the raw score mean difference suggests a large effect. If you look at the means, the mean difference is 10%, and this is an exam situation. So an exam score difference of 10% is a full grade. That's a situation where we can interpret the mean difference, and that's a pretty large effect. So yeah, C is your right answer. A is wrong because it's saying it's a medium effect, and it's not. It's large. And this is saying that the raw score mean difference is small. It's not. It's large again. And then this is saying it's medium, and they're not. They're both large. The mean difference and the D are always going to, if one is large, the other is going to be large. They're the same thing. They're just a mathematical conversion from one to the other. So it doesn't make sense to have one of them be labeled large and the other be labeled small. That's why D is helpful, because it helps you interpret the mean difference if you don't know how to interpret that mean difference. You're not changing the meaning, you're just giving yourself a way to give it meaning by using the standardized cut lines. Okay, next one, choose the best summary. B is the best answer. Confidence intervals indicate that our estimates of the parameters are not very precise. We say that because one of them is a small medium effect, and the upper bound is a very, very large effect. So that's a pretty wide range. So it's not very precise. And A is wrong because it says it is precise. And then it's also saying that it goes from large to very large. It doesn't. It goes from medium, small, medium to very large. And then C is wrong because it says we can say that that the effect is somewhere between small and large, and that's not true. And it says we can't be more precise than that. Well, we can, because the most likely answer is somewhere in the middle. The most likely effect size is a large effect, right? Because that's D. But it could be as small as a small medium effect, or a very large effect. So we can emphasize that values closer to the D that we actually observed are considered more plausible. Okay, in this one, they didn't randomly assign to condition. The researcher who did this didn't randomly assign, and that's going to dramatically decrease your confidence. Random assignment is very important. If you don't have that, you might not have initial equivalence. So this is a methodological concern. And so D is your right answer here. And now we're down to where we want to pick the right test statistic. I've tried to highlight in bold what the critical stuff is that helps you determine the correct answer. So in this case, it's an independent t-test. And the reason why is you have two groups. You've randomly decided to divide your group of 30 people into two groups of 15. So you have different people in the two different groups. So that's an independent t-test. This next situation is a related samples t-test. You're measuring the same group of people twice. So they record their number of nightmares for a month, then they take a treatment, and then they record it after they've had the treatment for a while. So that's the same people being measured twice. So that's a related samples t. This next one is a z for a sample mean. You have one sample mean, and that sample mean is a 71, and you're going to compare that to the population mean of 75.6, and we do know the population standard deviation. So when you have one sample mean and you're comparing it to some other number, and you do know the population mean, that would be a z for a sample mean. So you know the population mean, you know the population standard deviation, so it's a z for sample mean. Next one's a single sample t because you have just one sample mean, but you do not know the population standard deviation. So this is why it's different from the previous one. In the previous one, you knew the population standard deviation, so you could use a z for a sample mean. But in this case, you don't know the population standard deviation, and you're comparing one sample mean to some other value, so it's a single sample t. This final question is an independent t because you have two groups of people. Again, you have a group of Americans and a group of Europeans. Those are different people in the two groups, so it's an independent samples t. All right, I hope this will be enough to help you be very prepared for the exam. If you have any questions, feel free to contact your instructor.